Hey everyone, this is your section 2 of chapter 14 about solids, liquids, and gases. In section 2 of this chapter, we're going to talk about properties of fluids. So here are the things we're going to be talking about. We're going to go over Archimedes' principle, Pascal's principle, and Bernoulli's principle, all dealing with fluids. So the first one we're going to talk about is Archimedes' principle, and that deals with a question like this. How does something the size of an aircraft carrier float? So an aircraft carrier is the biggest ship that our Navy has, so it's going to weigh thousands of tons. So this is what we're talking about. It's the size of a small city. So the question is, how does something that huge float? And the answer is that there has to be some sort of a force pushing up on it from the liquid below in order for it to float. And that force is called buoyant force. And as long as that buoyant force coming up from the water is equal to the object's weight, the object, whatever it is, even as big as an aircraft carrier, will float. Buoyancy is the ability of a fluid, which can be a liquid or a gas, to exert an upward force on an object that is immersed in it, or in it, period. Now, as far as Archimedes' principle, what he found was that if the buoyant force on an object is equal to the weight of the fluid displaced by an object, it will float. However, if the weight of the water displaced is less than the weight of the object, it will sink. So as you can see here, the forces on the wood are equal to each other. The weight and the buoyant force are equal, which causes the wood to float. And then on the right-hand side with the steel, you can see that the weight force is much greater. You can tell by the length of the arrow than the buoyant force on the steel. So comparing buoyancy and weight, both displace the same amount of water in the picture because they're the same size objects. So the buoyant forces on both are equal, but one sinks and the other floats. And the answer is that the steel block weighs much more than the wood. So the gravitational force on the steel is much greater, while the buoyant force is still the same as it would be on the piece of wood. So to give you a little demonstration of Archimedes' principle, I'm going to let you guys watch this little video here. So back to our notes, we're going to go ahead and introduce density since we're talking about buoyancy. And another way to know whether an object will float or sink is to compare its density to the density of the fluid where it's placed. So in order to calculate the density of something, any object, you take its mass divided by its volume. And if the density of the object is less than the density of the fluid, then it's going to float. Now, water has a density of exactly 1. So anytime you have a density of greater than 1, that object is going to sink. Okay, switching gears to Pascal's principle. And Pascal talked about pressure in fluids specifically, and he actually has a unit named after him. You can have so many pascals of pressure. And Pascal's principle is that pressure applied to a fluid is transmitted throughout the fluid. So a good example of this that you see every day is in your toothpaste. If you squeeze the very end of the toothpaste, you know that the toothpaste is going to come out the nozzle at the other end because the pressure is being transmitted all the way through the tube. Pascal's principle is also seen in hydraulics. You push down the plunger on the left-hand side and the car will move up because that pressure moves all the way through the fluid. Another good example of this is in this next video that I have for you. So that video was a simple but perfect example of Pascal's principle. You could see that every time you push one plunger down, the other plunger would go up because the pressure was transmitted all the way through the water. And so pressure is defined as force exerted per unit area. This is how you could calculate it. And like I said, Pascal has a unit named after him. So if you're going to calculate pressure, you're going to put the unit of pascals next to it. Bernoulli is our last principle that we're going to talk about. And one part of Bernoulli's principle is that fluid velocity increases when the flow of the fluid is restricted. So I'm sure that several of you have used a garden hose before, and if you're trying to wash something off and you want greater pressure put on that water to help you wash something off, like your shoes, you put your finger over the end and the water starts going faster. That's a perfect example of Bernoulli's principle. When you put your finger over the end of the hose, the fluid is restricted, and that causes the velocity or speed of the water to increase. The other part of Bernoulli's principle is that velocity of a fluid increases. As it increases, the pressure exerted by that fluid decreases. And so this is something I would normally show you in class, but since this is a crazy world that we live in right now, I had to kind of show you a video of this really cool demonstration. So here you go. So there you have it. The only way to get the ball to go into the funnel, following those rules, was to actually blow into the funnel. No, he did not suck air in, he blew into the funnel. And if you have these things at home, I encourage you to try it because it's really, really fascinating and fun. So just need a funnel and a ping pong ball and you'll be able to see that it actually works. Our last thing that we're going to talk about is viscosity. And viscosity is the resistance of a fluid to flowing. So the higher the viscosity, the less that the fluid actually is able to flow, or the slower it flows. So something with high viscosity would be something like caramel or molasses, very difficult to pour. And then something with low viscosity would be water, that's very easy to pour, very quick. So in this picture right here, on all of these beakers were turned at the same time. You can see the turntable, and then you can also see how quickly these liquids poured. And you can see that this one went really fast, while this one still hasn't made it to the beaker. So this beaker right here, this fluid has high viscosity, while this one has low. And that is the end of your Section 2 notes. And I just want to tell you guys that I am very disappointed that we will not be going back to school. I know that some of you may not be, which is fine, but I have had a great year getting to know you guys, and I'm really sorry that I'm not going to be seeing you for these next couple of months. So I hope that you stay well, and I hope that you still explore some science with me in the next couple of months. But in any case, I just want you to stay well, and I'll see you next year.